I'm gonna just review two great articles, and next Saturday, I will talk about Markov chain, and I start a new set of lectures just about Markov chain mixing, coupling, path coupling, and spectral graph theory in general. So the article of today is written by Brice Sandland and Nalin Bahardovich, Antonio Lovet in 2020, and the title is A Simple Algorithm for Min Cuts in Near Linear Time. So a set of researchers who are very expert in data structures are writing a set of papers, very interesting papers, and very pragmatic because it can be scaled and it can be useful in practice. For example, it could be used for billions of nodes, so all of them are inspired by, of course, the work of Karger, which used a subroutine that finds a minimum cut, and that it too respects a given spanning tree. So the paper is the same as the Karger, but it is simplified, and as the title suggests, it is just a simplified version, and so it's the same result of Karger. So it takes this to find all minimum cuts, but their idea is to use heavy light decomposition. So they have the same result of Karger, but it is much more simplified than the complex algorithm of Karger. So they just want to combine the sampling idea of Karger and also tree packing of first started by people like Gabo. So they combine that, and so this is the Karger's near linear time minimum cut. And as you are familiar with, in the first stage of Karger's algorithm, you want to sample edge independently to form a graph edge. So it is just a sampling step. In step 2, we want to pack those spanning trees. So for example, if weight of trees having edge E is WT and that edge belongs to that tree, so these are the weights of the trees is upper bounded by the capacity of that edge. And so if we sample just O or log n of the trees from the weighted packing, a minimum cut in G to respects at least one of those sampled trees with very high probability. And the step 3 of the algorithm is finally, so we are given a spanning tree, and a procedure finds the minimum cut of G that too respects T, and we apply the procedure to all log n sampled spanning trees. The algorithm for obtaining, let's say, algo 1 is the algorithm for obtaining those tree packings. So we first initialize them. So the loading is 0. We have the partition is empty, and weight is 0. And then we repeat. We find minimum spanning tree with respect to this L, but we do it for all edges, and for all edges we say that the loading is increased by epsilon squared 3 ln of m for any edge in the tree. And if L of E, so this is increasing, so if L of E is greater than 1, then we return your W and P and anything. And of course, in each step, the weight of the tree is updated by the same things. And then we add the final tree T to the P. At each stage, we add the T to the partition. And when the number of trees is very, very small, is very low, then your bottleneck is very strong. You have a very bad bottleneck. But when you have more trees, you have lots of trees, then you can think that your bottleneck is weak. So when the number of trees grows, then the weight of the packing grows, and because of the duality, the mean cut value, it has a bigger value. The mean cut duality with the tree packing, and in algorithm 2, let's say, in algorithm 2, they form a graph G prime from G, and they find the smallest edge weight that has weight 1. So let U be upper bound for size of those mean cuts. And in second stage, we repeat. We construct H, and we draw it from the binomial distribution. P is equal to minimum of B over C prime and 1. And so we run the algorithm that I told you, algorithm 1, but this time on H. So the output is just a packing, a tree packing. So if packing has weight greater than 24B70, we set C prime to C prime over 6. And finally, we return some trees sampled uniformly at random. The interesting things in this paper is a review of Karger algorithm and how their simplified algorithm could show us a better understanding of what is going on. So algorithm 1 returns a weighted packing. Of weight is greater than 1 minus epsilon C over 2 in order of MC log n time. And the proof is very simple, because on each iteration the weight of some tree is increased by epsilon 2 over 3 ln of m. And because the weight of the resulting packing is bounded by C, so there are at most 3C ln of m over epsilon 2, which is order of C log n iterations. So the bottleneck in each iteration is the time to compute a minimum spanning tree. So this is the result of their algorithm, which is a simplified approach to the Karger's algorithm. But another article that I want to introduce is the work of Chandra Chakuri, Sudipto Guha, and Joseph Naor in 2006, which is called the Steiner K-cut problem. So this paper is cited by many researchers, especially by Chandra Chakuri himself, because in 2020 he wrote an article which generalized this article and used the result of his article. And so this paper is really essential for many directions. And the goal of this paper is that you have given a set of terminals. So now we have a set of terminals. We want to find the minimum weight set of edges that whose removal results in just k disconnected components, and each of them contains at least one terminal. So, for example, at least one terminal in each of them. And the solution is 2 minus 2 over x number of terminals approximation, and is based on just LP rounding. And it generalizes because the Steiner K-cut problem is very important, because it generalizes the K-cut problem and the multi-way cut problem. And let me just quickly review that in Vazirani as a good approximation for K-cut can be solved in polynomial time if you just fix your K. About multi-way cut, this is like CKR algorithm, which is a 1.5 minus 1 over K approximation. And multi-way cut is MP complete and APX hard, of course, for K greater than 3. And the other problem is Steiner K-cut. The same, it is MP complete and APX hard for K greater than 3. So this was just a quick review. Of course, the work of the multi-way cut is improved by Karger to 1.3438. Of course, minus epsilon K. It is improved. So now let T be a Steiner tree on terminal set X in G, such that whenever we say that D of E is 1, it is cut. And when you say D is 0, that element, that edge is not cut. So in any feasible Steiner K cut, at least K minus 1 edges of T. For example, for K equal to 3, we have some terminals here. And as you see, there are at least 2 edges that have to be cut. This edge and this edge. Let's see what happens for K equals to 4. So again, we have 4 disconnected things that we want to connect them. We have some terminals. And we try to connect them. So as you expect, this is K equal to 4, K minus 1 is become 3. So we need to cut 3 edges at least in order to make them disconnected. So that's why you understand why we want to write the minimum of why we want to minimize WED of E for any edge in your edges, such that the sum of the D of E, for example, this one, so there are 3 of them. So there are at least K minus 1 of them. So for any tree, any Steiner tree, this is a Steiner. Don't forget that it is not a spanning tree. Spanning tree is much easier than a Steiner tree. So for any Steiner tree, and this is just on terminals. So the tree is only on terminals. So this is you can think about it as the extension of K-cut of Naur and Rabbani. Then they use only spanning trees, not Steiner tree. and they provided a polynomial algorithm. But this problem is in general is NP hard, because we are talking about Steiner trees. So the easiest things that comes to your mind could be just use the spanning trees, because we understand it, we have polynomial algorithm for that, and this is the motivation that we just convert it to a problem, say K prime problem, that we want to minimize UV in E of G such that D of UV is greater than K minus 1, and UV is in edge of T for any tree such that T is a spanning tree on G of X, and D of UV some triangulation that we need, and of course some relaxation as usual, so it is continuous. And this is easy because we can solve it in polynomial time, because T is just spanning tree. So we can solve it in polynomial tree. So this is the trick. So this is the trick that they use. And for rounding the algorithm, they round it by just primal dual algorithm. So they round K prime to get to approximation for Steiner K cut. So the Steiner tree primal is just the minimum of d bar of E x of E over such that x of E is greater than 1 for any S which S separates x, and x of E is inside 0 and 1. So this is the Steiner tree primal. And so we use the technique of primal dual, Steiner tree dual. So the dual problem is just the maximum of y of s such that y of s is less than or equal to d bar of E, and y of s is greater than 0 for any s that separates x. And for solving this, they use the famous Goemans-Williams primal dual that incrementally grows dual solutions, and while they are maintaining that feasibility. And for example, S is just something that goes outside, and we have other things here. So for when I say for any S, it means that this S is separating your vertices. So this is the Steiner tree primal, and this is the Steiner tree dual. And as I've talked before, they used the primal dual paradigms in order to solve this problem. And you know that every cut that separates the terminal set has to be covered by at least one edge. And you see all of these dualities, set cover, all of these dualities are very helpful. So what Chandra Chakuri did is very interesting, that he has solved this Steiner K-cut problem by just trying to, because the Steiner K-cut problem is difficult and it's NP hard, so he approximated that in the first step by some spanning trees, and he used the result of that solution of that LP optimization to another optimization problem. So d bar of E is the solution of your LP minimization that you did for spanning tree. So it's like you have done